Hey everyone! Speaking with us today is Professor Tim Chen in the Department of Mechanical Engineering at the University of Houston. Professor Chen, would you like to tell us a bit more about your background in research?
Yeah, of course. Yeah, so thank you for inviting me to give this talk, and I hope whatever I have to say is useful to you guys. So I like you said, I started becoming a professor at the University of Houston starting August of last year, and I actually had a very let's say varied background in terms of where I was before. So it's not really a linear path that I followed, right? So I was born in China and I moved to Canada to attend high school, and then I did my university undergrad in at the University of Toronto in Toronto, and then I spent a year living in Chile in South America before moving to Holland to do my master's. And then I did my PhD in Switzerland. And finally, I arrived in the United States. So, in between those, of course, in between my studies, I also worked at engineering companies. And then finally decided this is kind of, at the moment, the thing that I want to do the most. This is not going to be, so I titled this Some Talks because it's not going to be a very technical presentation. It's more just to show you what I'm interested in doing and hope that sparks your interest as well. So basically what I said before, geographically, I've been quite diverse, right? So going from Shanghai to Toronto to Santiago to TU Delft, and then to ETH, and actually spent a summer in Caltech, and then to EPFL, and then finally to University of Houston. So, and I still don't know which place is the best for living yet, but I'm still trying to figure that out. But just to give you some idea what research is. As you're familiar with this movie, right? It's Frozen, I think, number two. And there was a number of research projects that went into making of this movie. So in particular, I would like to talk about how they simulated the movement of snow. So in this movie, in contrast to Frozen 1, you will notice that the snow got a lot more realistic. And this is from a technique that they used called material point method, that they're able to simulate individual snow particles and clumps of snow together to get a realistic feeling of how snow breaks apart and how snow merges together to form like a snowman. And why is that useful for real engineering tasks? Researchers were able to use exactly the same simulation actually, and simulate how avalanches happen in real life. And instead of a very coarse model of making a bunch of assumptions, they were actually able to use a supercomputer to simulate the real avalanche down to the particles of snow. So this image on the bottom left is not real. That's a simulation. And this allows us to use very different, I guess, advances in very different scientific areas to apply to different engineering problems. And this is not something that you learn in school, right? It really is driven by your curiosity to, knowing what happens in one completely different domain of research and applying it to another in a very innovative way. And so that's what I try to do as well. And so this is another movie called Big Hero 6, which inspired me a lot. It's kind of dark at this moment, but you can see the idea of forming structures from elemental particles and having these structures reconfigure themselves again and again to achieve different mechanical properties. So whether if you want a material to be stiffer or softer, what if you can have one material that intelligently can be programmed to do all of these things? Wouldn't that be great? Instead of having, like you have concrete, and it's always going to be concrete, right? And concrete, as you know, is pretty hard to recycle, especially reinforced concrete, because you have to take the steel out of it, and then you have to process the concrete. And the making of cement is extremely energy intensive because you have to heat this material to a very high temperature, etc., etc. So wouldn't it be nice if we can have material that can be readapted for different purposes? And this is a very lofty goal, but of course, we're nowhere near that point yet. So in terms of programmable matter, we study three different domains. Kind of the first is geometry. So how do we understand how geometry gets used in creating these structures? And the second, of course, we need some sort of material to make this thing. And the last is mechanics. So mechanics really just talks about if you punch something or if you push on something, how does that something react? Okay. And one more immediate thing that we talk about is a metamaterial. What is that? What is a metamaterial? A metamaterial is any material that we engineer to have a property that's not found in naturally occurring materials. So like that lattice you saw in the movie, right? That's not something you can find in nature, but that is something that we can manufacture using, let's say, a 3D printer or a bunch of other techniques. And this is one of the examples of a metamaterial that was made. So someone 3D printed this. What they wanted to show is typically when you squish something, when you push a piece of rubber, it typically expands in the lateral direction, right? You squish and it gets fatter. What they wanted to show is if they can create a material that when you squish it, it gets thinner in the other direction. And this actually creates a material that's much denser the more you push on it. And this is actually possible. So they showed this. And this is just one of the examples of exotic properties that we can get. And then there are several works, I would just show you some movies to show this. So we can make a flat structure that deploys into a 3D shape that we control just by changing the internal cut lines of a rubber sheet, for example. Again, the rubber itself is pretty conventional. You can buy it from Home Depot. But just by introducing these cut lines, we get a very novel structure. So, this looks kind of cool. We pull it apart and we see how it changes in geometry. And of course, if we just have an expanding sheet, it just gets bigger. Nothing really happens. It's not that interesting. But what we want to do is to figure out how do we make it go into 3D? How do we make a 2D sheet that goes into 3D? So we've taken a concept from cartography, which you've used if you look at a map, right? If you flatten the globe down to a 2D surface, there are some distortions that has to happen. Otherwise, your map will rip, right? So as you can see in this mapping technique, things like Greenland and north of Canada and Russia gets much bigger. So using this kind of concept, we're able to get structures that go from 2D to 3D. So this is one of the things that we can do. So we flat cut a piece of rubber, we just shake it, and it goes into 3D. And it stays there. And that's one of the novelties, right? Usually, if you consider any object, if you change the shape, it will go back to its original state. Good. The next thing we want to talk about is materials. So typically, materials are things you consider like steel, concrete, plastic. They don't change shape. But we're trying to make materials that change shape under some stimulus. So in this case, temperature. We can control at what temperature which materials change shape. And in this simple video, it just shows, at 40 degrees, the black material will change shape, the white material does not. And if you increase it to a higher temperature, they both will. So with this level of control, we want to show a solar panel deployment that avoids these damages that occur during typical deployments of existing solar panels. And this is kind of an analogy that we use, right? If you have ever played with silly putty, if you squeeze it pretty slowly, it's very malleable. If you hit it with a hammer, it's extremely brittle, or it just fracture into pieces. And we utilize this to create a structure that goes from a very small state to a very large state autonomously. So here's the video. And you can see just by submerging it to an elevated temperature, in this case about 40 degrees, which we intend solar irradiation will heat this up to around that temperature at a minimum. it may go higher, right? Depending on which way you're facing the sun, it may go much higher. But at a minimum, that's the temperature it will go, and it's able to deploy under, of course, environment that lacks gravity. And so these are just some of the research that we want to do, building it piece by piece to create that grand vision that I stated at the beginning. Yeah, so thank you very much. And you can ask me any questions.
Yeah, so I can begin our Q&A section with
Yeah, sure.
Yeah, the first question we had was like, what got you first interested in performing research with metamaterials?
That's okay, so like the example I showed you, right? I thought it was really cool to be able to exhibit some sort of very funky properties that you cannot get, right? Because well, for the first question, we need material to make any engineering things. And typically we start by selecting the material. As an engineer, right? You get a booklet almost, and you select the material you need, whether it's steel, whether it's concrete or wood or any material, right? You source this from nature. Wouldn't it be great if we have, instead of being dictated by the material choice, what if we can say, you know, this is the property we want, let's make a material that gets us that property. That will give us a lot more freedom in creating novel structures or systems. Yeah.
Okay, got it.
Mm-hmm.
Yeah, that's really interesting. Yeah, and what challenges do you face when dealing with such metamaterials?
So nothing in particular, right? Like, I mean, I can go into the technical challenges, which there are twofolds, right? One is it's a lot more complex, as in, okay, we're not at a level where we can build metamaterials like materials. As in, we cannot lay atoms atom by atom to make steel. We can't do this yet, right? So, I mean, people are trying, but that's really a far off goal. So, fabrication-wise, that's impossible, and design-wise, that's also impossible, because imagine, like, in gram of steel, you have, I think, 10 to the 23rd iron atoms. There's no way a computer can design such a thing. So these are the two main challenges that we deal with daily, right? Like, whether we can make this thing, whether we can even design the thing we want to make. So both of these are getting better, right? Like 3D printers are being able to do more and more resolution with more and more elemental particles or like materials that you can buy, right? So they're getting better, and computers are getting faster and faster. Algorithms are getting faster. But so that's the technical response to your answer, to your question. But then the more intellectually, like, doing research is difficult because we don't know what we're doing, right? We don't know what we want to do or how to do it. So that's something we have to define as we go. It's pretty open-ended, as in, it's not like an engineering project where at least you're told you need to make this turbine, right? At least that one end of that chain is known. But now we don't even know what we're doing. Yeah.
Okay, that's really interesting. And a follow-up question related to that is, what drives your research in the Architecture Intelligent Matter Lab?
The honest answer. Well, okay, part of it is curiosity. So there are just questions like the one I showed, right? That grand vision, that's the ultimate driver. But that's very far off, right? That's not something I can do in the next 5 years. But a more immediate answer is, there are practical questions that people with money want to have an answer to. And we have the technical expertise to solve those problems. And these are more concrete problems. And these are the things that we can solve, and those are the things we do. Right? So it's a two-part thing. We're driven by curiosity because we want to solve these grand challenges, and we're also driven by what's useful in a more immediate future. Because we're engineers. Like, at the end of the day, I'm trained as an engineer, right? I cannot do science for the sake of just doing science.
Okay, that makes sense. And one more question I had is, what do you think the best way for high schoolers to get involved with mechanical engineering?
That's very good. Okay, first thing is to show initiative, right? So I actually, this past summer, had a high school student who worked as a research assistant in my lab for 3 months, no, 2 months. And she did actually a lot. And I was extremely impressed by the amount of work she did and how much she could understand. But it really happened serendipitously. Right? Like, I didn't have a standard way of recruiting high school students. There's really no gateway that allows you to come to research. So it takes quite a bit of effort from both sides to say, there's opportunity available, and you have to commit to a summer of doing research, right? And it may not be the most fun summer you will have. But yeah, that's in terms of research. In terms of so it is also useful for high school students to know that to have research experience is quite beneficial for your college application. So especially if in the future that ends up being a publication that you can have, right? And that's definitely a leg up in terms of the schools you apply to. So there's definitely benefits, but it takes quite a bit of initiative to email, because there's many universities around you, and there's many professors in many universities, and a lot of them don't read their emails. That's just an interesting. It takes some persistence, and I do, like, institutionally, I try to collaborate with some high schools to allow them to at least have an easier time to know that there's some positions available that you can come and spend a summer and work with me or a PhD student in solving a more manageable chunk of problems.
Yeah, that sounds really great. Yeah. And well, everyone, thank you so much for watching our interview with Professor Chen. Take care, and we'll see you all next time.